My name is Dr. Jonathan McDonough, and I am a lecturer in the School of Engineering at Newcastle University, conducting research within the Process Intensification group. In this short video, I'm just going to give a very quick overview of how I use 3D printing in my research. I'll talk about what some of the future impact areas for 3D printing are, and finally, I'll address some of the broad challenge areas. So very quickly, I use 3D printing in my research to create chemical reactor geometries that would be simply impossible to fabricate or very impractical to fabricate via conventional means. So some recent examples of this include a very complex coiled reactor structure, as well as the miniaturization of a swirling fluidized bed technology. Here you can see an example of a very complex reactor geometry that we 3D printed. This shows a helical coil channel containing a secondary coil, enabling very complex flow patterns to be produced to improve our chemical reaction mixing. And you can see here that this would be very difficult to fabricate via conventional means. This shows a computer-aided design model of a swirling fluidized bed design that we received from one of our industrial collaborators, and this shows the 3D printed prototype. And through experiments, we were able to demonstrate that this swirling fluidized bed technology does work at this small scale, and this was actually the smallest scale this technology has ever been demonstrated at. There are a number of ways in which 3D printing will have impact in the future. The design freedom of 3D printing is the main advantage, and it's my belief that this is going to lead to a paradigm shift in the way we think about equipment design. And this is because 3D printing provides access to a very large geometric space of potential unexplored opportunity, where within this space there will be some exploitable geometry enabling us to realize performance benefits. This will then place increased emphasis on computer-aided design and 3D printing literacy for chemical engineering students in the future. Another area where 3D printing will have impact is on multifunctional equipment. So this is equipment that serves dual purposes, such as reactor separators and heat exchanger reactors, and then this will lead to increased multidisciplinary and interdisciplinary research. 3D printing will also lead to a reduction of physical inventory of bespoke replacement parts, and then this could have a deglobalization effect where supply chains become more localized as chemical plants start 3D printing their own replacement parts on site instead of relying on the existing transport infrastructures. 3D printing will also enable debottlenecking of small, unusual envelopes. So if there's a small space on a chemical plant, we could theoretically 3D print something to fit within this small space to realize improved performance, such as fitting a heat exchanger onto an existing reactor where there may not be space to do it via conventional means. We'll also integrate 3D printing and 3D printed equipment with other intensification concepts to realize further performance benefits. And finally, we'll see increased 3D printing onto existing surfaces for either part repair or augmentation. There are four broad challenge areas affecting 3D printing. The first of these is IP protection. 3D printing is a digital technology because it enables an almost seamless transition from a digital model into its physical counterpart. And because it's so easy to share and manipulate these digital files, it will become difficult for some companies to potentially manage and control their IP. So in the future, we may see more emphasis on brand and expertise recognition rather than on specific engineering IP. The second main challenge area is acceptance and certification. So although 3D printing enables us to print highly customized parts with almost no effect on the build time, the burden of customization may just shift onto the certification stage because bespoke equipment designs will require bespoke testing, and this could introduce additional time delays into the development and manufacturing cycle. The third challenge area is scale up, and there are three different facets to this. So firstly, 3D printing is geared towards small-scale prototyping, and it won't be able to rival mass manufacturing, such as injection molding technologies. Secondly, with regard to the physical scale of these printers, making the printers bigger will just increase the probability of reliability issues, meaning we may have to see increased focus on modular designs in order to scale up to the scales necessary for chemical production plants with 3D printing. And finally, another consequence of scale up is the CAD models themselves will become much larger, potentially on the orders of gigabytes and terabytes, which may make handling these digital files quite difficult in the future. The final challenge area is materials, because most of the materials manufacturers supply only proprietary materials, and there's no standardization, which may make research and development slower. Especially when the material properties are highly important to the performance of the particular equipment.